Okay, welcome back to part 2 of this lecture after the breather. We were discussing about the admissible set C here, okay. So, the admissible set C of all the stresses which basically includes the boundary of C for which plasticity can occur, but if the stress is strictly inside C, in the interior of C, then there will be no plasticity. Okay, it is elastic response, purely elastic response. Now, we were talking about the convexity. I am sorry, this is basically there is a small typo. So, basically this is C. Okay. So, the convexity of the C implies, you know about the definition of convexity. In case you did not, so I will explain. So, suppose this is a set C. So, this is the boundary of the set, right, and you have the interior points here. So, take any two elements of this C, each element of this C, because C consists of stresses, right. So, any point of C like this point, this will be a stress, call it sigma 1. Okay, take another point here, this is sigma 2, correct. So, these are the elements of the set C. Now, if it is convex, then if you join these two stresses by a straight line, which is done here, okay, to get another new stress anywhere within this straight line like this or like that, then these stresses, these are the interpolated stresses, they will definitely belong to C, they cannot go outside. Think about the possibility of the other possibility in which C is non-convex. Think of this apple shaped thing. So, take a stress sigma 1 here and sigma 2 here, join it by a straight line, and you will see that this point, for example, has gone out. So, this is not a convex set. Okay. So, basically the convexity of the set is a very important property of the boundary of the yield surface and also of the elastic region. Why is it an important property? Because it ensures uniqueness of solutions, and most importantly it ensures stability. Okay. So, I will tell you what basically I mean by stability here. So, you think about the situation in which this is the case, okay, this is the case, that is C is non-convex. Then it turns out that even though sigma 1 and sigma 2 are strictly within C, their interpolated version, which is in between, produces an inadmissible sigma, right, because it is outside C. That is not likely to happen, right, but there is a more compelling reason that I will tell you now. Think about this situation in which the sigma 1 comes very close, and so I will redraw this slightly, you know, this part I will just redraw a bit, okay. So, think about this situation, okay. So, it goes on like this, okay, I am not drawing the whole thing. So, let us say sigma 1 is here and sigma 2 is here, they are very close to each other, right. So, sigma 1 is just inside the boundary, just inside, not exactly on the boundary, just inside in the elastic regime. Let us say sigma 2 is also just inside, almost, I mean plastic plus, but not yet, it is just in the elastic regime. Then its interpolation means another point here, right, that is very close to sigma 1 and sigma 2 interpolated. So, both sigma 1 and sigma 2 gave you elastic response, whereas this sigma 3 gave you a completely inadmissible thing. That is not what actually the smoothness that you expect of the material response typically, and evidenced in experiments also, they indicate, right. So, this is where the stability issue comes in. Now, I will consider these aspects in more detail as we go along. So, you know, we can actually show that if the response of the plastic flow is rate independent, then it implies convexity of C, okay. We will come to this. So, convexity is a property, as we have already indicated, of both the elastic zone, the elastic region, and the bounding yield surface. Okay? And as we will be showing later on, convexity implies non-negativity of dissipation. If you have a non-convex sea admissible set, then well, you have to be very careful about the second law of thermodynamics, which may get violated. Okay? So, these are the issues. Now, let us talk about one of such yield criterion, F sigma. Yield criterion means specifying the function F sigma, F as a function of stress. This is called the von Mises criterion, pretty famous. Okay? This is given by F sigma equals square root of 3 by 2, the inner product of sigma 0, the volume the deviatoric stress, inner product with the deviatoric stress itself, minus some material constant sigma y. You can look at sigma y as the yield stress. Okay? It is a scalar yield stress. I mean, roughly look at it as some kind of an yield stress, okay, where the first yielding occurs. So, this F sigma therefore has to be less than equal to 0, right. So, sigma y is a material parameter, it is a scalar measure of the yield stress, right. You now should recall that any 3 by 3 such 3 tensor like sigma has 3 invariants, right. The first invariant being the trace, the third invariant being the determinant of the tensor. The second invariant is basically half of the inner product of sigma 0 with itself, the Frobenius product, right. And if you call it as J2, then you can see that F sigma is something like, this term is something like this term is equal to square root of 3 J2 if just minus sigma y, of course, that I did not write. Okay. So, basically what actually is happening is that this is an equivalent statement of the same thing. So, basically what is happening here is that the way that we have defined the yield function, there is one criterion in the definition, that is this quantity, the Frobenius inner product of sigma 0 with itself will remain the same irrespective of how whether you have rotated the coordinate frame or not. Okay? They remain the same. So, because it is one of the invariants, related to one of the invariants. So, this is an important thing. You typically define the yield function using invariants, which ensures that under rotations, rigid rotations of the coordinate frames in your body, it does not matter. I mean, the F sigma will remain the same. Now, let us come to the normalization factor, that square root 3 by 2. Where did it come from? Okay, so, that you can actually see by a calibration against a standard one dimensional tension experiment, right. Let us consider a sigma 0, a stress tensor deviatoric part, in which all the elements are 0 except for the first, this element, the first sigma 1 1, which is equal to S. Okay? Sigma 1 1 is S. You got the point. So, sigma 1 1 is S. All the other sigma ij's are 0. For that, if you now, this is the stress tensor, right, original stress tensor. For this, the deviatoric stress tensor will be simply as written here, okay, this quantity. All right. So, now if you take the inner product of the deviatoric stress tensor with itself, you will be getting something like 2 by 3 S square. Recall that sigma 1 1 is equal to S. Assume that S is greater than 0. So, it is tension. So, this is 2 by 3 S square. Now, if you were to define, suppose we drop that factor 3 by 2. So, define the yield surface without that factor. Then it means just by putting this fact that square root of sigma 0 inner product with itself is 2 by 3 S square, we see that S will be equal to square root of 3 by 2 times sigma y, which is when the yielding occurs. That means in a one dimensional experiment, even though we thought sigma y will be the yield stress, yielding is actually occurring at square root of 3 by 2 sigma y. That is non-intuitive, no, that hurts the model itself, the modeling purpose itself, right. So therefore this factor 3 by 2 corrects this is for the calibration. All right. So here is basically the typical structure. So you can see from here, from this von Mises structure, that it has a circular shape. If you plot the von Mises, plasticity, the yield function now. So what are these? Sigma 1 is the principal, sigma 1, sigma 2, sigma 3. This is sigma 2. I am afraid this is sigma 2, okay, and this is sigma 2 and this is sigma 3. So if you plot, okay, so if you plot this this stress, the F sigma, not in the usual stress space but in the space of principal stresses. So sigma 1, sigma 2, sigma 3 are the 3 principal stresses for sigma 0, right. And then you will see that the hydrostatic axis, which is given by sigma 1 equal to sigma 2 equal to sigma 3, that will come in such a, because it does not affect, the hydrostatic forces do not affect the von Mises plasticity, right. So therefore it comes in this way, it comes, so you get the overall, the yield surface as a cylinder, which is shown here, and this this sigma 1, the hydrostatic axis comes symmetrically as the center line of that cylinder, as the axis of that cylinder. That means irrespective of where you choose the pressure, whether it is this or this, it is basically the same cross section that you get, right, which is a circle, correct, the same circle that you get. So basically if you actually, so therefore von Mises's, the yield surface looks like a sphere in the appropriate space in the, so basically it looks like a sphere C, its boundary is spherical, okay. So this is the basic idea. Now it turns out that the von Mises plasticity is not adequate in many cases. What is important here is to understand is that in many cases you actually have multiple mechanisms at the microscopic level which inform plasticity, that means which drive plasticity. You do one experiment, one mechanism will be active. Now you try to repeat the same experiment, you will see in another experiment another mechanism may become active, right, because they are all competing with each other. In such cases a smooth yield surface as shown here will be inappropriate, okay. The reason for this we will come to soon, but in such cases a non-smooth yield surface would be better. For example, an yield surface of this type, right. So this is non-smooth at these points, right, okay, at these corners or at these vertices. This is a hexagon, So it is not just, it is important, see, it is not just from the mathematical perspective that this is interesting. It reflects the physics of possible indeterminism of certain competing mechanisms, which one will be predominant, okay. So we will come to the details later on, but for the time being the Tresca plasticity, Tresca yield criterion is an attempt to actually account for that aspect. So basically here again let us talk about the principal stresses only, right. So if sigma I equal to 1, 2, 3 are the 3 principal stresses of the stress tensor, then the F sigma, the basically the yield function will now be given by the maximum value of the difference between sigma I and sigma j for all ij minus some 2 tau y, where this tau y is a material constant, it is related to the yield shear stress, okay. So it is just a material constant. Again you observe that irrespective of how you choose your coordinate axis, if two such choices are related through a rotational transformation, a rigid rotational transformation, then this F sigma remains unaffected by the choice of the specific coordinate system, right. So, in a reduced dimensional setting, it is indeed true that the Tresca plasticity gives an yield surface, the C, its projection on a proper plane will be basically a hexagon, right. So, these corners that we have indicated, these correspond to the pure shear stress, right. You recall Moore's circle, right. The surface is still convex, right. It is still a convex surface, and the region, elastic region, is still convex. But also you should remember here that just like von Mises, Tresca yield surface is also pressure insensitive, because if there is a pressure, then it will just be added. So, sigma I for each I will become sigma I plus the pressure, right. So, you are taking the difference, sigma I minus sigma j, both will be translated by P. So, therefore, P will cancel, and therefore, it is pressure independent, right, just as we had in the case of von Mises plasticity. Now, if you take a look again at this overall, the F sigma in the sigma 1, sigma 2, sigma 3 plane, okay, then you will see again a similar structure. It almost looks like a cylinder, except that at any cross section it is a hexagon, right. That is why I drew that hexagon in the previous page. So, you can understand these edges which are coming now, right, these edges are these locations of non-smoothness, right. And as before, as in the von Mises case, this pressure, the hydrostatic axis, this is the hydrostatic axis, right. So, I have indicated this here, I have also indicated this here, okay. So, this hydrostatic axis goes through as if it is the center line of that structure, right, cylinder like, but not exactly a cylinder, okay, that hexagonal structure, yeah, that polytope. So, so far we have discussed two such yield surfaces, yield functions, which are pressure independent. But it turns out that pressure does have a role in many cases. For example, in soil, or rocks, in concretes of different mixes, polymers, right. Even in metals under very high temperature possibly, okay, they could exhibit strong sensitivity to hydrostatic stresses. So, therefore, the dependence of the yield function on the hydrostatic stress is also important, okay. Now, why is it actually needed? So, I mean, from a purely physical perspective, you may actually come to the conclusion just by thinking that compressive pressure, if there is a large compressive pressure, it may inhibit yielding, because it may close the voids, okay. It may close the interfaces, and therefore inhibit the yielding, because the yielding typically occurs through those points, either the interfaces or the voids, etc. Okay. But by the same logic, or the converse of the same logic, it therefore turns out that the tensile pressure should be able to promote plasticity, right. So, in such cases, materials such as soils and rocks which show pressure dependence, we can actually come up with another notion of the yield function F sigma, which is called the Drucker-Prager yield function, which is given here. Again, this is the inner product of sigma 0, which is the deviatoric stress with itself with a square root, as we had in the von Mises case, except for the factor 3/2, which are taken care of by these material constants alpha and k, okay. And then there is an extra term alpha times p, p is the pressure, and a third constant, second constant k, okay. So, F sigma therefore as usual should be less than equal to 0. This accounts for hydrostatic sensitivity, correct. Now the question is, how does it look like? So here the yield behavior changes depending on P. So let us assume that positive P means tension, tensile hydrostatic stress. Negative P implies compressive hydrostatic stress. Okay? So then rewrite F sigma equal to 0 in this manner. F sigma, as we indicated in the last page, you rewrite this as square root of sigma 0 inner product with itself equal to k minus alpha p. Now this is the radius of a circle whose radius depends on p, correct. So if p, which is, if it is positive, that is if it is tensile, then it reduces the radius if alpha is greater than 0, which is indeed true. Alpha and both the parameters are greater than 0. Okay. So if P is negative, that is compressive, then it increases the radius. This is also correct because of the fact that if there is tensile P, then as we discussed just now, it may ease plasticity, therefore the radius of that yield surface will be smaller. Yielding will occur early, okay, and just the opposite for compressive cases. Okay, so so what will be the representation of it in the sigma 1, sigma 2, sigma 3 space? So that will be now a cone, right, instead of, because along the hydrostatic axis you have basically a situation in which you have a cone like structure. The radius of the circle in the positive P will reduce. In the negative side, which is this side, it will increase. In the positive side, it will reduce. Okay? So that is a cone, and the elastic zone is enclosed by this cone, right. So if you actually plot this for two different P's, let us say P1 and P2, P2 is greater than P1, then for P1 you would have a circle like this, this is for P1. For P2 you will see a circle concentric but of a lower radius. Okay. So anyway, this is something that we actually often use in the context of pressure dependent plasticity, right. So we have already seen therefore that yield set C is convex and closed. Okay. We will soon use the notion of convex analysis, some theory, some theoretical aspect, some tools from convex analysis to understand it better. And we will see that another way of defining plasticity is through dissipation potential, completely independent way of defining plasticity, not by initially defining an yield surface. Instead, we can define a dissipation potential which in turn will lead us to the yield surface. Okay. So we will also be discussing soon, not in this class, but we will soon be discussing about the normality rules and the associated flow. Okay, when we discuss the flow rule, so far we have been discussing only about the yield surface. Now the yield surface is in the stress space, as I have been telling you. Okay. Now the associated flow, the flow rule for example, is a relationship between the stress, between basically the stress and the plastic strain rate. So we need to carefully define the plastic strain rate first in the context of small deformation and then go to that. Okay, so it is still premature to talk about flow rules. But let us, of course, we can talk briefly about the limitations of a sharp yield surface, right. So we have already been talking about it in one of the slides. So real materials basically exhibit gradual transitions. And as I have been saying that the stress relaxation time, if it is very large for metals under normal temperature range, not very large, okay, it is typically true. In such cases, there is no problem, but if for many such problems, in which the stress relaxation is really a fact, then we should not be working with yield surfaces. We should be actually talking of a viscoplastic Even though we call it a regularization, it is a physically admissible regularization of the mechanics. That means plasticity starts right from the beginning, however small this externally applied force be, but it picks up at a certain value or a certain region of the force, externally applied force, right. So, there is no strict yield point here, okay, that defines, or yield surface that defines plasticity. Okay. So, there is no need for a strict separation in this case. So, but there is one very interesting thing with this yield surface. It may be an idealization, in some cases a good idealization, but it offers a very powerful insight through the mathematical tools, insight into the physics through the mathematical tools of convex analysis. It is not just something that I am saying, I will be showing you how, okay, into the mechanics of solids, mechanics of plasticity. It offers a strong, very useful insight. So, we will actually from the next, in the next lecture onwards, specifically immediately in the next lecture, we will be talking of the plastic flow rule and the additive decomposition of the small strain. But just before that, we have actually not done one thing which we will have to do. Okay. So, that is, we will have to have a very powerful tool which is called the Coleman-Knoll procedure, through which we will be able to naturally maintain, whilst constructing our constitutive relations such as the flow rule and things like that, we will be able to naturally maintain the thermodynamic consistency. That is, the thermodynamic consistency means that the conformity of your formulation with the two laws of thermodynamics. For example, if dissipation turns out to be negative, then this is an inconsistency, right. How do you check it? Or how do you in fact do your formulation such that the dissipation automatically is ensured to be always positive or 0, okay. So, this can be very easily done and a very seamlessly done using the Coleman-Knoll procedure. So, we will have to discuss that and then go into the flow rule, okay, in the next class. So, for now this would be enough. Thank you very much for your attention and see you in the next class. Thank you.